this computer. Okay, now we are recording. Okay, so welcome to the first lecture in robot motion planning, MCTE 521, second semester in Botswana International University of Science and Technology. This is our first lecture, and this is Introduction to Robotics. So the question first is, what is robotics? So robotics deals with intelligent systems that are capable of manipulating things. Okay, so these intelligent systems that are capable of manipulating things are what we call robots. Okay, so our robots are this. Normally, when we talk about robots, we talk about this one is not hiding. I should hide. Taskbar should auto hide. It doesn't. Okay, anyway. So this is Asimo by Honda Robot, the first humanoid robot that is quite impressive. I think around 2001 and 2002. I have seen it when it was first released in the ICRA conference in Washington, D.C. And yeah, it was the most advanced humanoid robot. Humanoid meaning it's like a human. Yeah. And then this is another robot. I forgot the name, but it is not about intelligence. It is more of the expression and the movement to be human-like. Okay. And this is another robot, the Robo Dog by Boston Dynamics. And this is the humanoid robot by Boston Dynamics. These robots are considered to be the most advanced robots nowadays by Boston Dynamics. They are capable of moving many difficult maneuvers in terms of walking, jumping, and flipping. Compared to Asimo, the movement of Asimo is very primitive, but the most advanced Asimo movement before, when it was first demonstrated, it was able to climb up stairs. But nowadays, we will show some of the videos of Boston Dynamics that are much more advanced. So there are three major components of a robot. The first component, there are three components: computer, software, and mechanical. So these three components are unique to robotics. Some of the robots, they say there are robots that are crawlers or software robots that will crawl in the keywords in the internet and to collect them into a database for searching. Those are robots, but those are not robots in our sense. The robotics in this case, in our area, is that there should be a mechanical part. That mechanical part is the one that's responsible for manipulation or actuation. And then it has software and computer. So these two components are the ones that are responsible for intelligence. So the computer is like a brain, okay? And then the software is the intelligence. So what's the difference between the brain and the intelligence? Well, we are born with brains, okay? And so those brains, as we learn and we accumulate experience and knowledge, becomes the software that provides us with our intelligence. So the computer is the brain, which can have basic things. As we progress with our life, we accumulate intelligence, we accumulate experience and knowledge and expertise, and that's what constitutes our intelligence. And so this software that drives the intelligence keeps on changing as we accumulate more and more experience, more and more information. We can also be, unlearning certain things, and so the dynamics of the intelligence goes with the software. The computer is always there and it's hardwired already when we are born. Okay, and so in this class, because all these things are much more complicated systems, the one that I showed you, okay, we will start with a very basic study on robotic arm. And this is the concentration of this class, on how we are going to compute, or how we're going to compute the necessary mathematical equations and representations in order to control this robotic arm. This is the two basic components of the robotic arm, is that it has a base and it has a hand. The hand is also called an end effector. So this hand movement with respect to the base is what we are dealing with in this class. Okay, so you have any question to this slide? None. Okay, let's continue. So let's see some of the let's see some of the basic information on robot control. So robotics is considered to be, it is a very it is the heart of intelligence research. Okay, because robots in this case, we also say that mechanical systems or biological systems need brain in order for them to move. Okay, for example, in this case, the tunicates. The tunicates is like some sea organism that when settles down, okay, it has some brain when still looking for a place to settle down. Once it's settled down, they say the tunicates will digest or eat their own brains. They eat their own brains because they settled down already. They don't need it. Okay, so it means that what movement is really, brain is necessary for organisms or for things to move, because it needs processing, it needs a decision-making process, where to move and what kind of movement it's necessary in order to finally, in this case, the tourniquets to settle down. So once movement is gone, you don't need brains. Okay, so that's why the tourniquet eats its own brain. So the motion, the driving force, motion is the driving force to develop intelligence, like planning and decision making, and then what kind of movement and where it should go given this situation. Perception and knowing. Perception is like knowing, be able to be aware, or you perceive your environment and you perceive yourself to be able to be capable of doing certain things. Spatial representation, that means the space. How do you represent the space or your environment? Those are the information that are necessary for something to move. So planning and deciding, that is on the brain itself. Perception is how that organism sees itself with respect to the environment, and spatial representation is how the environment looks like. Okay, so there is itself and the environment. Okay, and then the decision making, the intelligence of itself. Okay, those are three main components for this thing to be able to move. Manipulation requires knowledge of the real world. So that the same thing, movement is akin to manipulation. In terms of manipulation, you also need these three things that we mentioned here. Manipulation is when you manipulate objects. You grasp certain things and you put it somewhere. Okay, so the ultimate goal of robotics is to create machines with human capabilities. Okay, really in the 1960s, when people are still doing robotics in the primitive sense, the goal, their dream is to have robot maids that don't cry. Okay, because sometimes when you have somebody working for you and they cry, you can get affected. And also, dealing with all these human things can be not very productive, especially if you just want to get things done. So if you have a robot maid, then it doesn't have any emotion. It will just do things no matter what you ask that robot to do. And other intelligent machines that can help humans. Okay, not just robot machines with human capabilities, but also other machines that will be able to help humans. Okay, that is what that we consider as the ultimate goal of robotics. So now let's look at some of the examples of state of the art robot nowadays. Okay, let's enjoy these movies. This is a robot soldier by Boston Dynamics. Okay, and they're testing it and showing a video of its capability. Okay, that's a very impressive maneuver. Okay, when Boston Dynamics first started, they are a company that is based in Massachusetts, and some of those principles I'm very familiar with because some of their students are coming from Stanford, and that professor also trained me somehow when I was studying in Singapore, National University of Singapore. Nowadays, they're becoming more and more advanced. That I think some basic principles are still there, but some capabilities are much more advanced compared to before. That's impressive. Okay, it's really impressive. I mean, machines really has very good capabilities despite all these disturbances. That's very scary. That's very scary. Things can fail, but for sure, these guys, I think they tested the system, and it doesn't fail in that sense. So that's why they're quite confident. But it can be very scary. I'm sure this guy has something inside to protect itself in case things fail. Nothing. Have you seen his tummy? There's nothing. Yeah, nothing. They're so confident that things don't fail. Anyway, that's impressive. There's nothing there.
Maybe there is legs.
It's scary. Okay, I never trust my robot like that. No. No. I have worked with robots many times, and then they can become uncontrolled. But for them, I don't know what they have. I mean, just for them to be very confident with their robots, I don't trust them. Anyway, that's very impressive. You see, they have the same clothes, but he knows where is the human and which one is not human. And these are just vision disturbances. You see, that guy also. Jesus. You see, it's so scary. But anyway, I'm sure they tested it because that, the principle behind here. You know how it is able to detect the not human, although they look the same. How? What do you think?
Artificial intelligence.
Huh? How do this guy, the robot, determine that it's not human? And this is the one that it can hit. Look at the guy. That's very scary. There, you see, he was so frightened. He thought it's him. How? It's by thermal camera. I'm sure there's a thermal camera there. Okay. I mean, when you see heat, it should avoid something that generates heat. Okay, because that's human. Okay. Anyway, so that one I believe. This one I believe, and then That one, I don't know. I don't know how true is that in terms of running. It looks fake to me, but I don't know if it's true.
It is fake. It was done by Korudo.
The running part. Okay. Anyway, so some of
Oh,
them,
really?
okay, unless you really interact with them, and we can see if they're true or not. Okay. So, but most of the things are true, I think. Okay, so that's Boston Dynamics. Let's go back. Now, are you familiar with Jimmy Fallon? Yeah, for sure. Yeah, you follow him. Okay, so this is a TV show where he showed some of the robots that people like to interact with. I've seen that guy. He visited. I've seen him in ICRA conference. He's from South Korea. He visited also in Italy when I was there, and he showed this. He's very good in these motors. He created his own motors. That's why they are very. Agile. I mean, the ability of the motors of these joints. Created these motors as well as joints, because in robotics the motors are joints. It moves the joints, sorry. And then here, because it created your own motors, you can be very, very strong, but then also very, very light, and have those capabilities necessary to have this cheetah move. Okay. Okay. The biggest capability of this cheetah robot is the running part and this agility part. It's not much about interacting with just like the Boston Dynamics robots in terms of interacting with disturbances and other humans. Now there's this. This is a tomato robot. Yeah, I like Japanese because they're crazy. And you're hungry for tomatoes, and what are you gonna do? We can't be jogging using it. I would love to see this. Sure, I would love to. Wow. Switch it on. Switchy. That's how they say the switch in the Japanese and South Korea. Switchy. It's not switch. So switchy on. The switch is on, and then it gives the tomato. Okay, so it's very simple, and then it's crazy idea. But that's how the Japanese are. They have many crazy ideas. Out of those 1,000 crazy ideas, something good, something really good will come out. Now let's go to the last one, Sofia. Okay, so you know Sofia. I'm sure you know Sofia, and this is the artificial intelligence robot, and it's capable of learning many things. It's not about manipulation, but Sofia is experiment on the intelligence part, on the artificial intelligence part. So hopefully, I don't know what Sofia is capable now, but you know, out of these things, they're saying before Sofia sounded like it's a pre-scripted. It's a scripted, you know, interaction. I don't know how far Sofia has gone now. Anyway, so that's okay. Yes, that's that. Next, okay. This is Boston Dynamics dancing. I wish I have a lot of things to. A lot of time for you to show some things. That's I really miss about America, you know. People are really having fun in the research there. They know how to make fun things out of what they're doing. That's a very difficult maneuver. Look at those joints. But I don't know. But I hope they will use my equation to make their maneuvering a lot more agile. I have a method to do that. Okay. Now the Davinci Surgery. I think you're familiar with this. I just want to highlight that this is, it started as a remote surgery, but remote because doctors are not available, you know, on a certain area. And so you need to have a doctor remotely just buy the robot, and then the doctor can remotely operate you. But because of communication, communication, you know, uncertainties and all these packages not coming in, it didn't make it in that process. So what happens now is that there's just a station. There is a station. This is the robot, and this is the station where the doctor is. Okay, that is the station, and this is where the robot, the patient, will operate. So the robot is just, I mean, the doctor is just there looking into the camera, because of course, you know, the machines, these robots will go underneath, inside the person's body, and then you cannot see that without looking through a camera. So the camera is just there in the same room. Okay, so this is the training of that robotic surgery. Okay, anyway, I don't have much time now, so I want to use the rest of the time to show you some of the research that I have done in this case. Okay, so first, please subscribe to my channel. Yeah, I have like a million followers now. You know, like 17 more students will become 1,017,000 subscribers. Please subscribe to my channel. So that's this is the thing. I mean, I will also upload this is the address of the channel. I will also upload the lecture videos there. Okay, so let's start with this work that I did with Professor Samakati from Stanford during my master's degree in Singapore. And this work is quite advanced even at that time. Nowadays, is still very much applicable. So what happens here is that there is this mobile base and this end effector that is exerting 10 Newton force on this aircraft canopy. So this aircraft canopy, we're supposed to grind it so that, or clean it at a very highly controlled force by around 10 newtons, and that's 1 kilogram. And so with these disturbances, the same thing. That's what I'm telling you about. It's the same principle as that Boston Dynamics, where something is doing this robot is doing something while I disturb it. I disturb the base randomly. The same thing is how the robots are being pushed. It's like this one is being pushed, and it will continue doing the work that is supposed to do, the work of doing polishing the canopy. Okay, that is year 2000, and I look very young there. I mean, I still not much of a difference now, but okay. So this is the one when you did something very good. Some people all over the world will come, and this is Kamakatib is my mentor. This is Tumizuka. This is the Puma robot, the same thing, and this is the base, and this is canopy, and this is Dr. Lim Sir-Yong, who is also in charge of the project. Dr. Professor Tumizuka from University of California, Berkeley, and this is Usama Khatib. And they went to see the Usama Khatib is the one who's teaching me. So Tumizuka just came because Usama Khatib was bragging about our results. So Professor Tumizuka came to look at it. And that's me. And this is a very basic control in terms of going through singularity. Okay, this is one of the critical control issues that roboticists have to deal with, the singularity. And it can ruin, or it can ruin some motion planning strategies. But in our case, it should not affect. The principle here is that it should not affect the control, even if the robot goes through singularity. Okay, that's I have to finish it. Okay, and next is this one is for my PhD work in Colorado. Which I started as PhD and finished as master's degree. Don't ask me why. It's been a painful experience for me. So now, so the issue here is that the robot will go through all these obstacles. It will start from here. This is the start location, and this is the goal location. So despite all these obstacles and the joints will fail, the robot can still move from here to there. So that's the point. The joints will fail, and there are obstacles in the environment. That's the problem. It's a difficult problem, but then there's a way to solve it. The way I solve it is going through the joint space, and there are some characteristics of motion planning in the joint space. We call it a failure tolerant surface. But anyway, if that failure tolerant surface exists, then it will guarantee that the robot can reach can successfully do from start location to the goal location, despite all these obstacles and despite the joints failing. Okay, that's the end configuration. Then we can start to see the failure movement. So joint 3 will fail, for example. Joint 3 has failed. This is the joint, and it's locked already, and then it's still be able to go into that place. I mean, to this location. Okay, and then some other joint failures. Okay. So you randomly fail some of the joints, and then it can still move there. Okay, and then avoid not hitting any of those obstacles. Anyway, that's finished. And then now is my work in IIT. where I work on dual arm manipulators. So now it's still using the same principles, but now it's becoming more, more complicated because you add more things to it. So this is just an equation that I developed when I was in Korea, and then I implemented it in Italy. And then in this case here, there are two arms, then one arm. These are just very simple movement, but you can see the forces that are generated. So this is the one that is complete equation that I developed, and this is an equation that other people has developed. So what I'm saying is that my equation is superior in terms of the forces. Okay, you can see the superiority of the equation, that is the robot is able to exert a force. This robot is exerting a force on the table, much more than this robot. They're using exactly the same control. The only difference is that there is a term that is missing in this control equation compared to mine. Okay, so that's one, and then the other one is using the same equation but on bipedal robot. So this is not done before. That's why I'm saying that if Boston Dynamics will use my equation using bipedal robot like this, then it can be though their humanoid robot can be more, it can do more things. It can be more agile because it releases the constraint in terms of the joints that you can use in terms of walking. So here, this is just a 3-joint robot. So this is 1 joint in the knee and 2 joint in the hips. And then here also 1 joint in the knee and 2 joint in the hips. So 3 joints that are moving. For other robots that are controlling, the way they're controlling now, it won't be able to walk and balance because of the way I move. I control the relative movement of the feet. Now it's able to walk and balance. If you use other control strategy, this kind of robot cannot walk. But I have shown that in this, using my equation, it can walk, given all these constraint of limited number of joints. Okay, it will continue walking. It can walk forever. Okay, that's one, and then this one is my my idea of combining from two robots to 4 robots. If you have seen Spider-Man, I think Spider-Man 2, where it has Dr. Octopus. I wanted to do something like that. Dr. Octopus has 4 arms behind himself. Okay, I wanted to control those 4 arms. So this is the way to control. I will tell Dr. Octopus, if you have 4 arms, we should use my equation and control your robot like this. Okay. Okay, and then lastly, this is not published yet, but these are results of my drone controller, and don't tell many people about it. Well, it's in YouTube. But anyway, this is my way of controlling drones. So if you see drones nowadays, I mean, that's Jacobian-based control. The way I want to do it is that here, when the drones move, you can see drones tilt. They will tilt when they have to move to the side, but I'm showing that in my case, it doesn't need to tilt. And also it's Jacobian-based control, so that I can attach an arm to the drone, so that it will be an aerial manipulation. But anyway, okay, I'm almost done. And then you can show that in this case here, it will tilt. It tilts and it can stay in the same location. If it was controlled the other way that drones are controlled now, if it tilts, it will continue moving. But for me, it tilts and stay there. Okay, and then I make the robot the drone more complicated. This is UMAV. There are 12 propellers there. So this UMAV drone will move and then tilt, but it will stay there. It stays there. Isn't it amazing? Oh, come on, give your professor a round of applause. Come on, you're not very convinced yourself. Are you convinced or not convinced? Yeah? Okay, let's turn off the Let's turn off the recording.